So let's go now, class, to heat exchangers. So this is the second of the four topics under part 1 of the review for unit operations for heat and mass transfer and separation processes. Now, heat exchangers that we will be discussing here is limited to the types and to the corresponding design considerations that we are to look into when we are going to design a particular heat exchanger. So in terms of the types of heat exchanger, one of the simplest and the cheapest type is the case of the double pipe arrangement. It's a case of two pipes or two concentric pipes in which you have a heating medium or a cooling medium in the annular space in between, and you have the other medium in the other fluid rather in the inner pipe. The fluid in the inner pipe is either to be heated or cooled depending on the objective. So this is a simple video on how a double pipe heat exchanger works. So you have the heating fluid on the annular space in between the pipes, and you have the fluid to be heated on the inside or passing through on the inner pipe rather. So this is counter current flow because the fluid to be heated and the heating medium faces each other, and in here this is the concurrent or the parallel flow because the heating fluid and the fluid to be heated are passing through the annular space and the tube concurrently, or shall we say parallel to each other or adjacent to each other, or in terms of the direction, they say they have the same direction as they enters the system of tubes. Now in some books it's represented as this, but this is more of the shell and tube type of heat exchanger representation. But this could be a case of a double pipe heat exchanger because you have a single tube here on the inside and you have the shell on the outer side, so it's still double pipe. Now, when you speak of the shell and tube heat exchanger, it's the modification of the simplest form wherein we have a bundle of tubes housed by a cylinder. So you have a bundle of tubes enclosed in a cylindrical shell. Now, these ends of the tubes are fitted into tube sheets, and they are separated through the shell itself. So the baffles are provided in the shell to direct the fluid flow, and of course as a form of support also for the bundle of tubes. So the case of the shell and tube type heat exchanger is this, and the one that you are seeing is the case of a one shell two tube pass heat exchanger. You have one shell and you have two sets of tubes. So two tubes passes. The fluid that enters here, this set of tubes still has to pass through this set of tubes. So two tube passes in one shell. So the fluid enters as a cold fluid but leaves as a hotter fluid because it's already in red. Your heating medium enters here through this particular portion of your shell and is guided in terms of its flow by the baffles. So it's the baffles that guides the flow of the fluid. So now it leaves this portion of your shell and tube type heat exchanger. Now this is a type of a one shell one tube pass. It doesn't mean that we have a one shell one tube heat exchanger scheme. In the shell and tube heat exchanger we have only one tube inside. If that is the case, we have a double pipe heat exchanger. But in here, you have one bundle of tubes. So it's referred to as one tube because one tube pass. Your fluid to be heated or cold is passing through in just one pass only, passing through this set of tubes. So that is why it's one shell, one tube. In simple orientation, this is it. You have this is your bundle of tubes, and this is your shell side fluid heating it. In the case of the 1-2, so you have one shell, two tube passes. So you see this? The fluid enters here to be heated or cooled, does not exit in this part but still has to pass through here. So it is being heated or cooled twice inside one shell. So a simple representation is this. You have this one tube pass, and this is your second tube pass, and this is your shell side fluid. In the case of a 1-2 shell and tube heat exchanger, we can have a 2 shell 4 tube system. So this is one shell here that you have on top, and this is another shell that you have here in the case of this one. So 2 shells, 4 tube passes, because in one shell your fluid is having 2 tube passes from here to here, so that's 2, and then entering on the second shell from here 3, and then here 4. So a total of 4 tube passes for your fluid to be heated. Now, in the case of plate and frame heat exchanger, you have a case of a plate, and then they are clamped together by a frame. So a gasketed plate heat exchanger consists of a stack of closely spaced thin plates clamped together in a frame. A thin gasket seals the plates round their edges, and the particular materials that being used here are the alloys, including stainless steel, aluminum, and titanium. In the case of this plate and frame heat exchanger, so it looks something like this, and the fluid to be heated passes through each of the plates, or is passing through in between the plates of this plate and frame heat exchanger. Now, a modification of this plate and frame heat exchanger is this one, the plate fin exchanger. So it's the same actually as the plate and frame heat exchanger. The difference only is in between your plates you have these corrugated sheets. So the plates are separated by corrugated sheets, which may form what we call the fins. In this particular setup, we refer to our block of plates as the matrix exchanger. So normally, the material used is aluminum, and they are joined and sealed by a bracing. And this is the case of the plate fin heat exchanger. So in between the plates, you have these corrugated sheets. So this particular orientation is cross flow. The fluid to be heated is the blue, and the red one is the heating medium. So they're flowing each other in a cross flow manner. This one is counterflow, just like the double pipe heat exchanger. The streams are facing each other as they leave or enters a particular section. So this is counterflow. A spiral heat exchanger is more or less like the plate and frame heat exchanger, only that this time your stuck plates were rolled. They were rolled to form spirals inside. So the fluids flow through the channels formed between the plates. It would look something like this. If you cut through here, you will simply have a case of a series of flat plates wherein they are clumped together. But if you roll them, it would form spirals like this. So your fluid passes through in the spaces in between the plates that were rolled. So this is for a spiral heat exchanger. Now, the next type of heat exchanger is the scrape surface exchanger. So its name already implies what we see in the exchanger. This could be viewed as a case of a double pipe, only that the inner pipe has an attachment. The attachment is in the form of a scraper. And this particular type of heat exchanger is used in the food industry, especially if we're dealing with viscous liquids. So typically, they are double pipe heat exchangers with fairly large central tubes in diameter jacketed with steam or cooling water. So your diameter range is from 100 to 300 mm. This is according to McCabe for this type of exchanger. And this is how it looks like. Okay? Your scrape surface heat exchanger. These are your scrapers that ensures that no amount of solid is remaining clinging to the tube wall. That is the outer tube. Now, what are the design equations needed for heat exchanger? So we have to consider what we call as the log mean temperature difference correction factor. The log mean temperature difference is actually this formula here. I will show to you the schematic in a little while on how do we account for delta T2 and delta T1. But this is the delta T log mean. In the case of heat exchangers, there are correction factors that are to be needed when we do the actual design. So this correction factor will account for the non-similar temperature regimes of the fluid inside the heat exchanger. So in that case, we need to convert from the delta T log mean formula to the delta T mean formula. And this delta T mean formula will be the formula that we will be using here in the Q equation, the rate of heat transfer equation. Whether we are solving it basing on the inside part of the heat exchanger or in the outer part of the heat exchanger. Now, the FT, the temperature correction factor, is taken from a diagram, an empirically set up diagram. So we will see that diagram in a little while. So from delta T log mean, we convert to delta T mean and use it in this formula. Now, what about the formula that you are seeing here on top? So in the case of heat transfer to and from the heating medium and to the medium to be heated, that would be this particular general equation. The rate of heat transfer is equal to the temperature driving force divided by the summation of all resistances to heat flow. Now, and speaking of that, whether we have this formula or a formula based on the inlet or the inside part of the tube or the outside part of the tube, all of this should be equal or the same. In the same way that the ratio of 1 over UA should also be the same. Now, the ratio of 1 over UA here, the product of UA rather, 1 over the product of UA is actually equal to the R. Now, this R, okay, I'd like to emphasize this R, if we have a case of convective heat transfer and conductive heat transfer, if you recall in your momentum transfer, all the resistances will be accounted for. So your R, or the summation of R specifically, will account for the heat transfer coefficient on the inside fluid, the resistance on the material offered by the material that separates the two fluid, and the resistance on the outer or the outside fluids clinging to the wall of that particular pipe in which heat is to pass through, going to or being transferred to the fluid that is to be heated in the inner wall. So outer to the inner part of the system of tubes. So this is how we account for the overall resistance. These two are convective resistances. This one is conductive resistance. Now, this is the formula, generic formula that was introduced to you in the concept of heat transfer in momentum transfer. Now, we go to how we determine the FT. Before we go to determining the FT, we need to know, by the way, the delta T2 and the delta T1, the delta T1 and the delta T2 based on the arrangement of our shell and tube type of heat exchanger. Because, by the way, the concept of the log mean temperature difference is applied to the shell and tube type of heat exchanger. So we have a different answer if the fluid is flowing countercurrent to each other in this case, or co-current in this case, and this one is countercurrent. So this would be how we will account for the delta T1 and the delta T2. H signifies or represents hot fluid. C represents cold fluid. In meaning that's the entering temperature, and out, that's the leaving temperature. Same thing in here. So the two differ because the delta T2 and the delta T1 here is not the same as the delta T1 and the delta T2 in here. So in your formula, though they are the same formula for two scenarios, the delta T log mean will not be equal if we are considering two different scenarios. Now, this one will be multiplied to Ft. Now, where will that Ft be taken? Now, this one is the temperature correction factor diagram. It depends, again, it depends on the scheme of your shell and tube type of heat exchanger. If it's a 1-2 and 1-4 type of heat exchanger, you will have a different diagram for that. If it's a 2-4 heat exchanger, a different diagram for that. Now, what do you have in this diagram? On the horizontal axis, you have the Y. On the curves, you have the Z. How do you determine the Y and the Z? You base it on the temperatures of your hot and your cold fluid. It necessitates, or it requires, that your temperatures for all your streams should be known. This method will not be able to give you the actual amount of heat transfer rate when either one of the four temperatures are unknown. So you can determine one if unknown and the rest of the three is given by using energy balance. That is, amount of heat from the heating medium is equal to the amount of heat absorbed by the cooling medium. That way, you'll be able to complete the four temperatures for you to be able to solve for the Y and the Z. So if you already have the Y and the Z, I think it's self-explanatory. You can get the temperature correction factor basing on the orientation that is specified in the problem. Now, the question is, what if our answer is 1.8? Or what if our answer is 2.5? You will approximate in your curves here where is 2.5 most likely to be drawn. And then that's where you're going to stop when you already know the Y value in your projection going up. And then with the temperature correction factor on the vertical axis. That's how you use this particular set of diagrams together with the formula for delta T log mean to get the amount of heat that is transferred, either on the inside fluid or on the outside fluid, depending on what the problem requires. Nonetheless, whether we're computing based on the inside fluid or the outside fluid, the amount of heat transferred should be equal at all times. Okay, now, what about if your temperatures are not complete and there is no way that you can complete it? So an example is when you're only given two inlet temperatures and you're not given the outlet temperatures of your fluids. You cannot use the LMTD method or the log mean temperature difference method. There is another method that you can use, and that particular method is the heat exchanger effectiveness. And take note when you can use this: when you don't have all four temperatures known, or you only have the two, the other twos are unknown. If you do energy balance, you cannot still complete it if you only have two known values of temperature. At least you should have three for you to know the fourth one. What is this heat exchanger effectiveness? This is the ratio of the actual amount of heat transfer in a given heat exchanger to the maximum possible amount of heat transfer if an infinite heat transfer area were available. Or shall we say, if there's just enough or more than enough amount of heat transfer area available, what is the maximum amount of heat that could be transferred. That should be our numerator, and the actual, that should be our denominator rather, and the actual would be our numerator. Now, in the case of heat exchanger effectiveness, let's say for example, this is the schematic. You have cold fluid entering here, and this is the outlet temperature. This is your hot fluid inlet temperature, and this is your outlet fluid temperature. These two fluids have their corresponding C sub H or C sub C. Specific heat of the hot fluid and specific heat of the cold fluid. In the case that we're in, we want to transfer energy from the hot fluid to the cold fluid, it's a must that C sub H should be greater than C sub C. Now, in this scenario, we have this formula. Actually, whether it's counterflow or co-current flow, the same formula should be used. The amount of heat that is transferred by the heating medium or the hot fluid should be the same amount of heat that will be received or absorbed by the cold fluid. So we equate it. If we have equated the two, this Q that you got will be the same Q that could be computed if we use the effectiveness concept. So effectiveness times the C minimum times the difference of the two inlet temperatures of the hot and the cold fluid. So if only two are given here, specifically you only have this and this, how will you be able to get the Q? You cannot. So that is why you are provided with the formula in here using the effectiveness, the heat exchanger effectiveness. What do we need to find the heat exchanger effectiveness? For countercurrent flow, the effectiveness is solved using this formula. You have in this formula UA, heat transfer coefficient, overall heat transfer coefficient, and this is the area, C mean, and C max. What is C mean and C max? C mean and C max are simply the product of the mass transfer rate and the CP of the cold and hot fluid respectively. So it's just actually your CP multiplied to M. Now you just multiply, you just substitute the two here, and you will have the effectiveness of your heat exchanger, wherein the pattern of flow of the fluids or contacting of the two fluids is countercurrent. However, when you need to find this effectiveness, it's only good if you have already everything in this formula. What about if you don't have it? Then that brings about the use of the NTU, the number of transfer units. The number of transfer units is equal to UAC minimum. You will need this in order for you to get the effectiveness. The same thing with these two, for you to be able to get the effectiveness, especially if the effectiveness cannot be analytically determined using this formula. Then that brings about another diagram, empirically made diagram, for us to be able to determine the effectiveness. The case of co-current flow, we have a simpler formula for effectiveness. In this formula, we have the same representation for C min, C max, and NTU. Now, this is the diagram that I'm referring to that you will be using so that you'll be able to find the effectiveness. The curves actually is equal to C minimum over C maximum. And you have the NTU here, which has the UA divided by C minimum, so that you'll get the effectiveness. Okay? The heat exchanger effectiveness. If you have the heat exchanger effectiveness already, then you can know the rate of heat transfer using the effectiveness method. Now, there is this problem in heat exchanger we call heat exchanger fouling. Now, the fouling is brought about brought about rather by material deposits on hot surfaces, especially on the annular space in between the two tubes, if the heating medium is on passing through the annular space. And or it could be on the inner tube also, if your inner tubes have feed or fluids that are processed which have solids. So if these solids get deposited on the side walls, on the walls of the cylindrical tubes, they will have what we call, or they will have this occurrence of what we call fouling. And rusted impurities can also be considered as fouling materials. And the strong effect of boiling, when there is turbulence inside the tube during boiling, then the corrosion inside the tubes would be higher, then there's a greater tendency for fouling to be occurred. In that case, then the scales that are forming here, or in here you have already the scales, you have scale here and you have scale here, they will add resistance to heat transfer. So the resistance to heat transfer that before you considered is only on the inner part of the tube, on the outer part of the tube, and on this conductivity resistance offered by the material between the two fluids. That's the original thing that we account in terms of the total resistances, as discussed to you in the previous slide. When there is fouling, you have to add the resistances caused by fouling. And these are the fouling matters here that already deposited in the tube. How do we explain that in terms of a formula? This is your original formula. This is your summation of resistances that I just mentioned a while ago. And in the formula of the cylinder, you will be using the area log mean in the middle part here, in the conductive part of the summation of R. Where is that, miss? Here it is. This is the conductive part of the resistance. This is the convective part of the resistance. Convective because it has something to do with fluid flow. Conductive because this has something to do with the characteristic of the material separating these two fluids. If there is no fouling, this is only your summation of resistance. This is only your summation of resistances. If there is fouling, you have to add this. The fouling caused by the deposit on the inner part of the tube, the fouling caused by the deposit on the outer part of the tube. If the problem is silent about fouling, then use this formula for the U sub I, or the heat transfer coefficient, or overall heat transfer coefficient of the inner fluid, or of the fluid in the inner tube. Amo ni siya. But if there's fouling, you have to account for the fouling materials. Okay? Now, here, again, is a set of problems on heat exchangers that you can add to the problems that you already have learned before regarding heat exchangers. So it has the application of the effectiveness. It has, I think, the application also of the log mean, temperature difference. So they are good examples for you to look into in terms of the concept that I have discussed in here. Okay. And that would be, I think, and this would be, I think, the end of the slide on heat exchangers.